Hello, my name is Renan Cavenaghi Silva, and together with Professor Douglas Domingues Bueno and Professor Rodrigo Borges Santos, we are going to present our work entitled Disturbance Observer of an UAV with a Suspended Payload. Unmanned aerial vehicles, or UAV, are a type of aerial robots that are being envisioned to realize different applications, such as photography, surveillance, parcel delivery, and dangerous applications as firefighting and spying. The use of UAV is motivated due to the lower cost, versatility, and ease of operation comparison with their many counterparts. Besides the wide range of applications, the mission objective is normally achieved by the transported equipment, such as a camera, a crop spraying system, or a parcel in the case of aerial deliveries. A typical mission is illustrated in Figure 1, where it can be divided in 5 parts: takeoff, cruise, the mission path, return, and landing. To realize the mission, the controller, also known as an autopilot, uses a reference dynamical model to calculate adequate inputs to move the vehicle to the desired trajectories. However, disturbances such as model dynamics, model uncertainties, and external forces reduces the controller performance and can even destabilize the system. In the Disturbance Observer-based control, a Disturbance Observer can be designed to estimate the disturbances, which can be compensated by the controller, improving the tracking performance. This approach is summarized in the figure. Based on the trajectory error, the controller calculates an input based on the previous estimate. The control input is applied to the system, which is also influenced by the external disturbances. The system output and the control input are sent to the Disturbance Observer, which is responsible for calculating a new estimate of the disturbances. In this work, we are interested in estimating the disturbances forces acting on the simulated UAV and payload dynamics using the Disturbance Observer. The remaining of this presentation is divided in 3 parts: methodology, results, and conclusions. A common type of UAV is the one with rotary wing, such as the helicopter and the multirotors. This type of UAVs are known for their higher mobility, featuring vertical takeoff and landing, and also hover capabilities. The multirotor type have gained attention to their low cost and mechanical simplicity, which comes from the possibility of controlling the altitude and attitude of the vehicle by simply changing the angular velocity of each rotor. The simulation model consists of a multirotor UAV with a suspended payload. The UAV has mass m, and the payload is assumed to be a particle of mass mp, which is suspended by a rigid rod of length L. The payload's position relative to the UAV is parameterized using 2 angular coordinates alpha and beta. This particular choice of parameterization is performed to avoid singularity in the mass matrix during simulations. The equations of motion are obtained by applying the Euler-Lagrange equations for each generalized coordinate. The result is a system of n second-order differential equations that represent the dynamics of the system. To solve numerically, a new variable v equals dot q is defined, and the system can be written as a system of 2n first-order differential equations. This system can be represented as a nonlinear function of the state x, the inputs u, and the disturbances du. To design the Disturbance Observer, the linearized equations of motion are required. To obtain the coefficients a, bu, and bd, the Taylor expansion of the function f is realized around the equilibrium stage. The Disturbance Observer design objective is to reduce the estimation error, which is defined as the difference between the estimated disturbances and the applied disturbances. The Disturbance Observer can be designed according to the reference by choosing an auxiliary variable z such that its dynamics is expressed as a function of the state and the inputs. The error dynamics is determined by the time derivative of the disturbance estimation error. Assuming that the applied disturbance is constant, the result is that the error dynamics can be expressed as a function of the rate of the auxiliary variable plus the transformed velocity. Substituting the definitions and simplifying the equations, the disturbance estimation error can be converged to 0. By choosing an observer matrix gain L such that the matrix minus LBD have eigenvalues in the left half of the complex plane. The controller is responsible for calculating adequate inputs so that the system trajectories will follow the mission trajectories. The disturbance compensation using the observer is realized by including the estimates in the control algorithm. The desired acceleration in the underactuated directions are now adjusted to include the disturbance estimates. The modified acceleration are then used to calculate the attitude required for the vehicle to project the lift in its underactuated directions. To demonstrate the methodology of using the disturbance observers, the UAV and payload system are simulated using the Runge-Kutta algorithm for two different conditions. The first is the Heveran condition, where the disturbance is not compensated. The second, denominated the observed condition, the disturbance estimate is compensated in the control loop. As disturbance sources, a constant weight field is assumed, which results in a force acting on both the UAV and the payload. The simulation parameters are presented in the table. Considered parameters, a suitable disturbance observer gain matrix is selected by arbitrarily choosing the coefficients such that the matrix minus LPD have eigenvalues in the left half of the complex plane. The presented figure shows the simulated trajectories. It's possible to see a slight improvement of the trajectories from the observed case in the x, y, and z directions. The trajectories are also shown in the 3D space, where the trajectories of the payload are also displayed. The disturbances from the observer condition are presented in this slide. For the I and j directions, the estimated disturbances shown in continuous lines approaches the actual disturbances shown in the dashed lines. However, for the k direction, the disturbance estimate is different from the applied disturbance. This can be a result of the assumption of linearized dynamics to calculate the disturbance estimate, where the nonlinear neglected terms act as model disturbances. In summary, the performance increase using the disturbance observer is calculated using the presented performance metrics, which evaluate the trajectory error as function of time. The table shows the calculated metrics for the observer condition are improved in comparison with the reference case. In conclusion, in this work, we designed a disturbance observer using the UAV and payload linearized dynamics. The disturbance observer is used to obtain an estimate of the disturbance forces acting on the system. By simulating a wind field and wind drag, the disturbance observer was successful in obtaining estimates of these external forces and unmodeled dynamics, which are then informed to the UAV controller that partially project the disturbances. The result of this approach is an improvement of the tracking performance. Further development is still required to deploy the disturbance observer in real applications. For future steps, we pretend to validate the approach in an experimental setup, testing for different vehicles, payloads, and environmental conditions. We are thankful to the GMC, CNPq, PPGAM, and the ONSP for supporting this work. I have for this presentation, and thank you for your attention.